All right, Geraint. So here we are. It's Christmas time in Australia. It is warm and humid, and it reminds us of that. There's a Dylan Moran quote we stuck in our first book, just basically saying that Australians walk around audibly crackling because we're about 3 miles from the sun. And yeah, it feels a bit like that at the moment. But that brings us to mind of actually, as things go around the cosmos, Earth is pretty nice. It's a pretty nice place. We always get asked, um, is there life elsewhere in the universe? And part of the answer to that is always going to be, well, in order to answer that, we're going to have to go look for whether there are other places which are accommodating to Earth in the universe. And there's a hypothesis that basically says, no, we're probably it. It's called the rare Earth hypothesis. What's going on there, Geraint? Take us through it.
Well, let's start with a scientific myth, right? I mean, if you read your history of science, written by scientists rather than historians, right?
Yeah.
There's this notion that the Earth has been steadily moved away from being the center of the universe. It used to think that the Earth was it, the universe is around us, but what we've found through our astronomical observations, of course, is that the sun is just a star. There are billions of stars in the galaxy. There are billions of galaxies in the universe. It seems that every star appears to have planets. So there's billions of planets, etc. And so you might think, based on the odds, based on the statistical odds, that life must be common, right? There's lots of planets, lots of stars. Earth isn't special. So should we expect life in the universe? And the rare Earth hypothesis actually turns that somewhat on its head and says that when you actually look at the details, when you look at the properties that this planet has, it might not be a typical kind of planet in the universe. It might be rare in terms of planets, and hence life itself might be rare.
Okay, so what is it about us, the Earth, that seems a bit rare?
Okay, let's start with some basic facts, right? Let's just say that I was going to get you, let's take all the stars in the universe, we're going to put them in a big bag, right? And I'm going to get you to put your hand in with a big glove on, of course, because they're going to be hot.
Good, hot.
And just grab a star at random.
Don't try this at home.
Yeah, grab a star at random, just any star. If I pick a star at random in the universe, what kind of star am I going to get? Is it going to be a star like the sun?
Probably not.
Probably not. Probably not. Because what we know, of course, is that the stars in the universe, their distribution, right, is also related to their mass. And it's the less massive stars are much, much more common than the more massive stars.
Right.
The sun isn't that massive, but it is also not amongst the least massive stars.
Right.
So the typical star in the universe is a red dwarf star.
So I pull my hand out and I get something smaller than the sun and redder than the sun.
That's right. So it has a mass roughly a tenth the mass of the sun, roughly. And so it's burning its nuclear reactions a lot slower than the sun. So it's a lot more feeble when it terms of its output. So when we look at things like, where is the habitable zone around that star? For a red dwarf star, it has to be a lot closer in because they put out a lot less energy.
Yeah.
And you already start to run into problems if you start to put planets in the habitable zones of red dwarfs. Number one, you're so close to the star is that your spin, the spin of your planet, gets locked into the orbit of the star. In the same way that we see the same face of the moon pointing towards the Earth, a planet orbiting a red dwarf is likely to have the same face pointing towards the star. So one side is going to be constantly daylight and baked. The other side is going to be constantly nighttime and dark. And so people have wondered if you could have life on those planets, maybe it's only in the twilight zone. I'm glad I said twilight zone. The twilight zone around the edge between the daylight and the night side.
Right. So basically, there's no day and night. There's just a day side and a night side.
Yeah.
And so the perfect place to stick your villa is right on the edge, and then maybe your villa just turns around, and so you get day and night just for you.
Yeah. Well, so the one way to think about this is not just about you enjoying the planet, but the chances of life arising on that planet, right? So, you've already reduced the surface of the planet, which you could have conditions where you would expect there to be life. The other thing is, and this was a nice result out of the University of Sydney last week, I believe it was, and you're going to link it here somewhere.
I will.
Right.
I'll be there.
This is one of these things that we've come to realize about red dwarf stars, is that they're bad-tempered little buggers.
Yeah.
Right. So in terms of things like solar storms and solar wind and all this kind of stuff, they tend to be a bit more active than the sun, which means that that planet, which is closer in, while it's getting less light, might be hit with more particles, right? So you might get more stuff raining down and making the planet uninhabitable.
Sort of high energy protons, electrons, gamma rays, all that sort of stuff.
Which are bad for life, right? Because they are things that break molecules apart. So it turns out that the vast majority of stars in the universe, the conditions you've got are not conducive for life, right?
Mm-hmm.
So typical stars, typical planets are unlikely to be good for life. On the other end of the scale,
Mm-hmm.
you've got the giant stars,
Mm-hmm.
right? So these are very, very massive stars whose temperatures tens of thousands of degrees. Their output, instead of being peaking in optical light, peaks in ultraviolet and into the X-ray and even gamma ray regimes.
Right.
Right. So if you have a planet going around those stars, then the sunlight that arrives is not the nice visible light that our molecules can use, etc., but it's high energy light, which can rip molecules apart.
Yeah, so there's a really interesting sort of coincidence here between the energy of the light put out by the sun and the sort of energy you need to power photosynthesis. And you might think, oh, whatever light the star put out, some process could use it. This is just evolutionary adaptation. Well, only within limits. So there is such a thing as the typical energy of a chemical bond, right? That's where you need to be. And if you're less than that, you don't break the bond in a way that allows you to power a chemical reaction. You just sort of wiggle the bond a bit. And that's basically what your microwave is doing, sort of. If you hit it with too much energy, you break all the bonds, and rather than just making a nice chemical reaction. So for example, when we see, there's a molecule in our eyes that straightens when a light particle hits it and then returns to its normal state. So we can't see radio waves because they don't straighten the molecule. They just make everything wiggle a bit. And we don't see X-rays because they would just break everything.
Absolutely.
You need that nice range. So yeah, the sun has that. These bigger stars have the sort of let's break everything apart wavelength.
Yep. Yeah. So we're already seeing that you can't have, well, you would think that life would not be common around the least massive and the most massive stars, and it's the stars in the middle that are the ones which you could expect the conditions right for life. But another interesting thing about the sun is it seems to be a relatively quiet star.
Mm-hmm.
When we look at other stars out there, many stars are variable in that their brightness changes, right? So they get brighter and fainter, and it might be a few percent, it might be 10%, but some of the bigger stars, they get brighter and fainter by huge amounts, which again, if you think about life on a planet, for us, we've got this constant stream of light from the sun, which is coming in nice and even. We're not swinging from being baked by the sun's rays to going into an ice age, being baked by the sun rays on time scales of, however long it takes stars to vary. So in terms of the sun, it already looks like it's not a typical star in the universe. It does have some properties which suggest that the environment of the solar system is more quiescent than many other stars. Mm-hmm. So this is what points towards this rare Earth hypothesis.
Okay. So that's the sort of rare nice star hypothesis, I suppose you could call that part of the equation. What about the Earth? What do planets need to do in order to be life permitting?
Right. So there's a lot of argument over this because, of course, we don't really understand how life started, right? So anything I say is hypothesis, right? It's nobody really knows. But there are some quirks that if you look at the Earth and you look at the other planets, right? So firstly, one of the things that's kind of interesting is that we still have ongoing plate tectonics. right? So we live on a planet where surface land is created and subducted, and there's this sort of chemical processing which is going on due to the fact that we have plate tectonics, which is related to the fact that the core of the Earth is liquid iron. And that produces heat, which produces plate tectonics. And when you look at Mars and you look at Venus, those processes have shut down.
Yeah.
Right. So they don't have this chemical reprocessing that the Earth has. And people think that that actually does play a role in the climate and the elements that are available on the Earth's surface.
Yeah. So I've heard, obviously not my field, but Australia has particularly poor soil quality relative to everywhere else, just because we don't really have that many volcanoes around us. We're not that close to the Pacific Rim volcanoes. Maybe Indonesia's the closest, but in other parts, a volcano might seem like a very destructive thing, but once it's rained down a whole bunch of ash on your fields and that's turned into soil again, you've suddenly got a whole bunch of chemicals, nutrients in the end, sort of going back through the cycle. They're sort of replenishing your soils against leaching away.
Yeah. So, Australia has some of the oldest rocks in the world. There's the Edicarian Hills, I think, in South Australia.
We'll look that up.
Probably, yeah, you can put a link somewhere. So one of the problems Australia has had is that it's an old continent, and it's had a long time for elements to leach out of the soil. And so we already know that as a farming country, it's actually not a good place to farm, right? The soils are not brilliant because there's not that replenishment from volcanoes, etc. The other thing, of course, that the molten core does for the Earth is that it generates an immense magnetic field. So the Earth has a very strong magnetic field. So you have currents going around in that metallic core, and that magnetic field is one of the things that protects us from the solar wind. The sun is still putting out these high energy particles, which hit the surface of Mercury and get down to the surface of Mars, etc. Earth, however, has a magnetic field that shields the surface of the Earth and protects us from these high energy particles. So again, when we look at the planets in the solar system, the fact that we still have a molten core, and I should mention that part of the reason we have a molten core is that there are radioactive elements still decaying in there, keeping the core warm. Replenishes the chemicals on the surface of the Earth, does stuff to the atmosphere, and produces a magnetic field that keeps the solar wind away. It already says that within the solar system, the Earth itself is now looking a bit like a lucky planet. I mean, if we were Venus, right? So we already know Venus is in trouble because it's already a lot closer to the sun. But we also know that if we pulled Venus back to where the Earth's orbit is, they're very similar masses. But somehow all of that plate tectonics and stuff shut down on Venus a long time ago. And it again would just have weathered soils, not good places for life.
Right.
So, and then there are other aspects of the Earth which are weird. Number one is the moon. Okay. Now, we know that moons are common in the solar system, in that Jupiter and Saturn have got more than 100 between them. But if you look at the rocky planets, only Earth has got a substantial moon, not counting Pluto in the outer solar system, right? Mars has got 2 rocks, which are effectively, they look like it captured asteroids.
Right.
The Earth has got a moon, which is an appreciable fraction of the mass of the Earth. And that is important. Now, we think that the fact we have a moon is an accident, right? Something happened to the Earth in its early formation where something struck it, big chunk of rock got ripped off, and that rock settled down to become the moon.
Right.
So, a chance encounter in the early life of the Earth.
As in an accident in the sense that you wouldn't expect something like the Earth's forming. So form the solar system again, you might get another Earth where it is, but to have something come along at just the right time to get the moon, that seems very rare.
Yeah. So it's one of those by chance events.
Right.
But the thing is the moon, it's played a big role in the life of the Earth, right? So there's a couple of issues. Number one is that the moon appears to have stabilized the rotation of the Earth.
Hmm.
Okay, so what we know is that if the Earth was spinning on its own, then there's weird interactions that can go on, and we could do an entire video on
Yeah.
spin interactions.
Yeah.
But it turns out like a spinning object on its own is not a stable thing, right? You can get rearrangements of mass, etc., and spins can flip. And there's a lovely video of one of these spinning devices on the space station.
Yeah. Yeah.
Maybe you can link to that.
I'll throw that in. That's really great.
Yeah, it just shows that something can spin, zip, 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 and then something goes zip, 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 zip,
Yeah.
zip, zip, and
I
it's
think Derek's got a really good video on that for Veritasium.
Yes. So spins can flip due to very small effects.
Hmm.
And it looks like that for the Earth, the spin orientation that north has been pointing towards that patch of the sky for a very long time. And part of that is to do with the spin interactions between the Earth and the moon. So again, if you think about it, if you imagine that you have an early Earth and life is forming on it, that, the fact that you've got an equatorial zone and a polar zone and well-defined climate zones is kind of nice. What would be bad is that if you have your North Pole and your South Pole and your equator, that suddenly there's a flip and the North Pole and the South Pole are now in the equator and the polar regions are now going to, it could really, really mess that up. And these timescales, could be as short as a few thousand years to flip from one thing to another. So the position of the moon, the location of the moon and its mass has helped the Earth have a stable climate and stable in inverted commas here, right?
Yeah.
Stable-ish climate over billions of years.
So I assume that's important for evolution, as it's trying to, if you can get organisms into a sort of niches, they can really start, that process of adaptation to really, so if you think about, the sorts of processes you hear about of a competition between species where they both ratchet their way up, the prey and the predator, they're running faster and then this one's running faster and they just keep ratcheting up. All of that relies on some degree of environmental stability. If suddenly they're all running on ice, all of that adaptation that went into their body plans, and it now sort of goes to waste.
Yeah. Look, I'm not an expert on evolutionary biology.
No, me neither.
But, I just in my mind can imagine that, yes, life adapts to even changing climate, but there must be a time scale, right? I mean, if the climate changed every week, then you think it would be hard for creatures to adapt to that kind of situation. And the moon also has captured a few of those asteroids that would be heading towards the Earth, right?
Yeah.
We do know that rocks still hit the Earth.
Mm-hmm.
The moon has saved us from some of those. But also importantly, and there's a big argument over this at the moment, is the role of Jupiter, the fact that we have one big massive planet in the solar system, and whether or not its gravitational field, effectively, has Jupiter taken more than one for the team?
Yeah.
Right? And when I was a young PhD student back in 1991 or 2, Schumacher-Levy 9, a comet that came into the inner solar system, we saw what Jupiter can do. On its first pass, Jupiter basically ripped that rock apart, and then the next pass, bang, Jupiter basically swallowed that icy, rocky, comety thing.
Right.
And that kind of object, if it hit the Earth, and there was no chance that Schumacher-Levy 9 was going to hit the Earth, but if that kind of object had hit the Earth, that's the kind of event which...
That's a Hollywood.
That's right.
Hollywood level event.
A Hollywood level event, right? So again, we're only now starting to get a picture of what other solar systems look like. There are massive planets there. We're trying to work out how, lots of them seem to have massive planets very close in, which does nothing to protect you from comets, right? Because you need you need a sentinel in the outer solar system, not something on the inner solar system.
Yeah.
So this question of, again, how much life on Earth is dependent on the fact that we had a Jupiter again, it's another one of those interesting questions.
So another interesting thing was part of the red dwarf discussion was you've one of the things you want Earth to do is we've got this nice atmosphere here, and you want to hold on to that because all that's holding that in is gravity, and so naturally, it's very easy for gas to leave the top. There's no lid on the atmosphere. And so lighter elements like hydrogen, if there was free hydrogen in our atmosphere or helium, it's probably floated off by now if there was any at the start. But how do we, we've held on to our atmosphere in the face of the sun pouring its solar wind at it and radiation at it. What sort of planets out there are going to have atmospheres? Do we have a good handle on that?
We don't. It's understanding where atmospheres come from is really not straightforward. I mean, in our solar system, you say that about the solar wind, right? But then we look at Venus, and Venus has got a lot more atmosphere than the Earth does, and it's closer to the sun.
Yeah.
But of course, the thing about Venus's atmosphere is it's carbon dioxide, right? It's essentially all carbon dioxide, which is a relatively heavy molecule, so it can hold on to that. Of course, our atmosphere has been shaped by the fact that we have life on the planet.
Yeah.
The fact that we have an oxygen and nitrogen-rich planet is related to the fact that we have plate tectonics, which recycle gases through the atmosphere, and life. The early atmosphere on Earth was probably a lot more like the atmosphere on Venus. And there was this event that occurred where basically this oxygen, which was a byproduct of the early life, came to dominate the atmosphere, right? So yeah, we really don't understand what atmospheres other planets could have, right? And even if they have atmospheres, if they do eventually get life, their atmospheres get shaped by life. But there's another question, is not only the atmosphere, but whether or not they have water.
Yeah, that's a crucial one.
Right. So, and again, this is one of the weird things about the Earth, and we don't think about it, I think. Here we are in Sydney, and you can see the ocean. And even though you and I know that 70% of the Earth's surface is water and only 30% is land, it feels like there's a lot of land, but most of it is water.
Yeah.
But similar to other kinds of coincidences we see, right? To an astronomer, 70-30, that's almost 50-50, right? Okay.
Good enough.
How come we're on a planet where there is a mix of land and ocean?
Yeah.
You would think that, again, if you could randomly grab planets, then either a planet you'd expect it to be either completely dry, or a complete water world.
Yeah.
So again, we don't quite understand how we got all the water on Earth. We think it was something to do with comets landing on the Earth. We actually think that the early Earth, during the initial periods, which are known as the Hadean, I do like that name, right? That the Earth was effectively a water world, right? Almost a water world with a little bit of land. But we're in this epoch now where we've got land and water. And if you talk to people who think about the origin of life, there's some people who wonder about deep sea vents, but other people, like even Darwin, wondered about these little pools,
little pond,
little pond, right, where you can collect salts and things, but you need tides.
Yes,
you need water to
Moon's
wash
back
in.
again.
Yeah, and the moon's back again. So the moon is essential for tides, but you need water to wash in to bring elements, and then you need a period where things can dry and consolidate before water washes back in again. So this mix of land and water looks like, again, it was an important one. And is that common? Is that rare? Again, if you played the flipping coins or grabbing planets at random, you'd expect desert worlds and water worlds. But in between worlds, maybe they're rarer.
Of course, plate tectonics comes back into that as well, because if you just flattened out the surface of the Earth, you could just put all the water on top of all the land, right?
Yeah.
It would cover it by, I think it's about a kilometer or something of water.
Yeah.
And so you need something to lift up the land in between the bits of water. Yeah, fascinating stuff.
So I think I did a calculation a while ago, and I might need to revisit this. I, I think if you either double or triple the amount of water on the Earth,
Hmm.
you would basically cover up to Mount Everest,
Okay. Yeah.
right? Because you have to remember that, yeah, again, it sounds weird, but we have to remember there's only 30% of the Earth's surface is land,
Yeah.
right? And a lot of that is relatively low lying. So,
Yeah.
if you know,
Australia's done.
yeah.
Yeah.
So we can do this, can't we? We'll scribble this down. Everest is about 9 kilometers high.
Something like that. Yeah.
Yeah. And we know what the surface of the Earth is.
Well, it's 6,300 kilometers in radius.
Yeah. Yeah.
So 4 pi times that.
And multiply that by 30%.
And he just gets out his scrap of paper. I might just put up a little screen here that just goes to black, and then sometime later,
Times 10.
Oh yeah, three. So yeah, 3 times.
Yeah. Hey! do 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 do.
Our time has run out, unfortunately, but you did get the answer in the end.
Yes. So there you go. I think that's isn't it? So we could go all the way back to what I said, that I did a calculation a while ago, and I think I calculated that if you increase the volume of water by a factor of 2 to 3, you would cover Everest.
Yes, good. Nailed it.
So we would have a complete water world with Kevin Costner in it. And so the question...
Never seen that movie.
Oh, okay. So the question is, when these comets were raining down, why did we get that amount of water that we did? Because in astronomical processes, right, you've got lots of things crashing around, etc. When you get things, a factor of 1 or 2 within a particular value that you think is interesting, then it does make you scratch your head a little bit, right?
Yeah.
So if we'd had, roughly 3, 4, 5, 6, 7, 8, 10 times the number of comets collide, would the Earth be a water world?
Yeah.
Yeah.
Just a couple more comets hit, and things are very different around here. Very interesting.
Yeah.
All right. Well, in the spirit of Christmas, it seems like we should all go and appreciate the Earth a bit, because it's a very wonderful place. It might be a rare Earth. That's the hypothesis that we're considering here. But whatever it is, it's the nicest place around. So Merry Christmas, everyone.
Merry Christmas.